Introduction. So I'm Satoshi Yoshida from the University of Tokyo, and this talk is about equivalence between two different tasks. And so first, so this is a beyond IID, so maybe you may expect me to present something about entropy, but unfortunately, I don't present about anything. And so relative entropy, and unfortunately no, and alpha z lambda conditional entropy, of course not. Okay, and the reason is like this. So the entropy, in my opinion, is like how to quantify some non-ideal, resource in a nice way. Like for instance, if you have some information source and if it's info distribution, then it can just describe as a log n bits. But if you have a non-uniform distribution, then you can represent it as a entropy of this distribution. So this is the reason why you need the entropy. But somehow in our work we consider some idealized case, so that's why we don't have entropy. Okay, so what this talk is about. So basically, in this talk we consider two tasks. One is in communication scenario, which is called a port-based teleportation, where Alice wants to send some quantum state to Bob. And the other is an estimation scenario, which is called a unitary estimation, where you want to estimate some input unitary is. And somehow we consider some idealized scenario, where for the communication scenario, we don't put any restriction on entanglement. So somehow we optimize over any entangled state. And for the estimation scenario, we consider the scenario where the input unitary operation is taken from some completely random distribution. But the good point is that in this idealized scenario, we can completely connect in these two completely different tasks. And this is on the level of the performance. And so basically, the main result is that if you calculate the optimal fidelity of this port-based teleportation and the unitary estimation, basically these are the equivalent. And this proof is somehow constructive in the sense that if you have some optimal protocol for one task, then we can construct the other protocol. Okay, so let me explain what the port-based teleportation is. And the history of the port-based teleportation dates back to the Nielsen Chan, basically. And Nielsen Chan considered the universal programming, which is a following idea. So the idea is like you want to choose the input state after choosing program state. Program. And more concretely, like you want to encode the information of some operation to the quantum state, which is called a program state. And by applying some unitary on input state and the program state, you want to apply the operation to the input state. This is the idea. But non-programming theorem prohibits its perfect implementation, so we can just consider probabilistic or non-exact implementation. And probabilistically, it can be done very easily. And one can done by using quantum teleportation. So if you have the choice state of a unitary operation instead of the Bell state, and we use this choice state to do a teleportation, then the quantum state you get is something like this. So like this xi is the input state, and you have some Pauli correction term and U. So if you post-select the measurement outcome, then basically you can apply this unitary to the input state. And yeah, of course, this success probability is 1 over d squared, but you can do that. And the important, this kind of protocol is also called a storage and retrieval, because this protocol can be decomposed into two stages, like storage stage and a retrieval stage. And the important thing here is that retrieval only succeeds when no correction is needed. And the port-based teleportation is basically the idea to extend this one to increase the success probability. And instead of having a Bell state, Alice and Bob shares some 2n qubit entangled state, like represented by psi. And first, Alice measures her input state and her share of the entangled state, and sends the measurement outcome to Bob. And depending on that measurement outcome, Bob chooses a port I and traces out other states. And if this teleportation succeeds, then basically we can use this one for the universal programming. Because if you apply quantum channel to this entangled state, basically doing the similar like a procedure, we can do a retrieval. So basically, port-based teleportation is a quantum teleportation without any power correction. So this is the idea. Okay. And we look at the optimality of these protocols, and we consider, as I said, we cannot do a perfect implementation, so we can just do probabilistic or non-exact. And we first see the probabilistic scenario, and for this one, we can consider the trade-off between query complexity and success probability. And it is known that optimal storage and retrieval of unitary is achieved via this PBT, port-based teleportation. And since port-based teleportation works for any channel, basically, port-based teleportation is actually optimal for storage and retrieval of any channel. And also, its optimal probability is explicitly given like this. So basically, for this probabilistic exact case, everything is known. So nothing to investigate more. But for the deterministic and non-exact case, the situations are different. And in this case, we consider the infidelity instead of the success probability. And for this case, optimal storage and retrieval of unitary is known to be achieved via estimation-based strategy, where you first estimate what this input unitary is, and then retrieve the unitary based on the classical estimate. But this estimation-based strategy is not good for any channel because estimation becomes harder for general channel. And actually, we have recently shown that it is suboptimal even for isometry channel. So even if we do not extend to any channel, it's not good. And so ideally, it will be good if we can do a storage and retrieval via port-based teleportation. And we have several stuff known in this field. And for port-based teleportation, its asymptotic fidelity was known in this Matescu-Chandler paper. And its scaling with respect to the number of ports n is known. And it's like n inverse square. And for the unitary estimation, we know more. And it depends. And for the number of queries n, the scaling of this infinity is the same, basically n inverse square. But we also know the dependency on d tight, d to the fourth. But for this port-based teleportation case, we don't know the dependency. We didn't know the dependency on d. So basically, the question here is, can we do optimal storage and retrieval protocol using port-based teleportation? And actually, our work basically positively answers this question. Okay, so this is the outline of talk, and I will formally define the task first. Okay, so for the port-based teleportation, as I said, Alice and Bob first shares this entangled state 5 PBT. And basically, the procedure I described can be written in the quantum circuit like this. So it's not very hard. It's kind of a bit generalization of the usual quantum teleportation circuit. And from this circuit, we can define a teleportation channel, which is given by the quantum state Bob obtained from Alice's input state. And using this teleportation, we can define the figure of merit as a channel fidelity between this teleportation channel and the identity channel. Okay, so this is for the port-based teleportation. And for the unitary estimation, we consider the following task. So suppose you are given some, suppose some unitary is drawn from her random measure, and you can access the black box implementing this corresponding unitary operation, and for multiple times like this. And the task is to estimate what this unitary is. And of course, you need to do that in a quantum circuit, and what you can do is basically something like this. And by using this one, we can define the guessing probability where, guess it to be the U hat given U. And by using this one, you can define the figure of merit to be an average case channel fidelity between the estimated unitary, and the true unitary, like this. So yeah, these are the definition of the task. And the important stuff here is that for the port-based teleportation and for the estimation, basically we can define similar fidelity measures, and that's why we can construct the correspondence. Okay, so I will present the main result. So basically, we consider the following. So for the port-based teleportation, we consider the teleportation of the d-dimensional system using n+1 ports. So we have 2n plus 2 entangled state. 2n plus 2 qubit entangled state in here. And for the estimation case, we want to estimate a d-dimensional unitary using n queries. And what we have shown is that by comparing these optimal fidelities, then these are equivalent. So this is the result. And what we can say from this one is that since we already know that optimal storage and retrieval for unitary is achieved via this unitary estimation, and by using this equivalence, we can construct a corresponding port-based teleportation protocol, and which is somehow near optimal because port-based teleportation basically by this correspondence, like a port-based teleportation achieved basically almost the same fidelity as the unitary estimation. So it's also near optimal. And the good point is that it works for any channel. So yeah, that's good. Okay, and as I said, we have also constructed. This proof is based on the construction. So we have constructed the conversion of any protocol implementing port-based teleportation to unitary estimation and vice versa. So in this way, we implemented a conversion between the protocols. So it's in the protocol level. Okay, and before going to the detail of the proof, I will show some of the applications of this work. And so basically, by using this one-to-one correspondence, any results known in the port-based teleportation can be translated to unitary estimation and vice versa. And this is a very good application of this work. And the first application is to show some asymptotically optimal port-based teleportation fidelity. And so it is already known that unitary estimation obeys the Heisenberg limit. Like for the number of queries n, it scales like n to the inverse square, and for the d, it scales like d to the 4, which is shown in Jan's paper and Hart's paper. Yeah. And by using our equivalence, basically we can show that port-based teleportation also obeys the same scaling, because if you remember the correspondence, you just change n to be n plus 1. So if you consider the asymptotic limit, there's no difference. And actually, this improves the previous result shown in Matej Crescendo paper, which shows tight scaling with respect to n, but not tight scaling with respect to d. So this improves over this one. And this partially also solves some open problem raised in this paper, like in the Matej Crescendo paper again, and which is to determine the coefficient with respect to this n inverse squared. And basically, our results show that this coefficient is given by HD, and its scaling with respect to D is perfectly determined. So yeah, though it's not exact yet, but yeah, this partially solves some of the parts. Yeah, and the other application is for unitary estimation, and so this is. So this is for the case where the number of queries n is not so large, like n is smaller than or equals to d minus 1 case. And in this case, we can exactly determine the optimal fidelity. And this can be shown using the corresponding result for the port-based teleportation. And yeah, maybe it's not very so. The one way to see this result is that basically, for instance, if n equals to d, then its estimation fidelity is still 1 over d. So like even if you have a number of query close to dimension, and if the dimension is like say exponentially large, in this case, even if you use exponentially many queries, you cannot achieve a very good fidelity. So this kind of thing is also shown. Okay, and we also have some application for the unitary inversion, which is to obtain the inverse operation of some unknown unitary operation. Yeah, I don't explain a lot for here, but if you're interested in, I can also explain offline. Yeah, so I will go to some of the proof techniques used in this work. Okay, so the proof basically proceeds like this. So first, utilizing the symmetry of the problem, we show that any protocol implementing this task can be reduced to a special type of protocol called a covariant protocol. And then we show the conversion between these covariant protocols. Okay, so first let's see the symmetry of the port-based teleportation first. And okay. So first of all, so you have a some entangled states, and basically any state can be represented by using the operator, basically using the inverse of the Chori representation, because like this, and the normalization condition of this vector can be written as a normalization condition on this operator, or basically. And by using this representation, the teleportation channel of the port-based teleportation can be written like this, like in a graphical case. Like here the input state is coming, and this is an entangled state, and you have a measurement, and you choose a port A here. So this is like this. And to calculate the teleportation fidelity, you need to take a channel fidelity between this one and the identity channel. And basically, this corresponds to like a wiring input and output wire like this. So we have this expression, and by rearranging these wirings, basically we obtain this expression. And if you define this red part as sigma A and this green part as pi tilde A, basically this fidelity is just the inner product between these two operators. And this sigma A is just some constant operator, and this pi tilde A is some operator you need to optimize. So the fidelity is like this, and so sigma A is defined like this. And if you if you consider the constraint on this operator pi tilde A, basically this is kind of generalized P of M, because this operator pi tilde A should be positive, and if you sum up over A, then you will get X tensor I, where X comes from O like this. So, and of course, X should be positive. And so, in this way, the optimization problem of the teleportation fidelity of port-based teleportation is given by this kind of STP, where you need to optimize over this pi tilde A. Okay. And the next step is to utilize the symmetry to reduce this SDP. And as you may notice, this operator sigma A has a very nice symmetry. And one comes from the unitary, one is the unitary group symmetry, and that comes from the U tensor U star symmetry of this maximally entangled state here. So if you apply U star and the U tensor N here, then it should be invariant. And the other symmetry is a permutation symmetry, where if you permute the system here, then this should correspond to permuting the index here. And by using these symmetries, we can show that the operator X here should satisfy the unitary group symmetry plus permutation group symmetry. And by using the sure-wire duality, this shows that X should be linear combination of the Young projector like this. And the important here is that, so basically, the degree of freedom of X is now represented as a number of, basically the numbers, like complex numbers. And it is also okay. And this is just for X, and X basically corresponding to O in this circuit. And you also need to optimize over this pi A, but it is known in Felix paper that you can always take a pretty good measurement, and a pretty good measurement always gives you the optimal fidelity for this case. So you don't need to care about measurement now. So this protocol is now just parameterized by this single, not single, but several parameters W. And if you calculate the fidelity, then this is given by some bilinear form, which I will show more detail in a couple of slides. Okay, and let's go on to the unitary estimation then. So we consider the most general case where you can do some adaptive strategy, which means that you have some input to unitary U, but you don't need to call it in parallel, but you can use it adaptively. So this is the most general circuit here. And this TU hat represents a quantum comb or quantum tester. And by using the Choi representation, basically this is given as an inner product of Choi of U and the Choi of this TU hat. But here, the input distribution is how measured, so it should satisfy some unitary group symmetry. And basically, if you apply V and W to the unitary, then this should correspond to, applying V and W to the, this estimate. So if you move this V to the other part, then this green part should be the same as the original TU hat. So if you define this operator, then this T satisfies a double unitary group symmetry. Okay? And by using this operator T, we can rewrite this expression like this. So first, we insert T square, square root of T and the inverse square root of T here. And by using this double unitary group symmetry, this square root of T commutes with this U. So you can derive this expression. And if you consider this blue part, and if you calculate the norm, then you can show that the norm of this part should be 1. So this actually gives you the valid quantum state. And you can also show that this orange part gives you the valid quantum P of n. So, we start is just a graphical representation of the Chori representation, but actually this part gives you the valid quantum circuit now. Okay, and by using the double unitary group symmetry, this operator T should be given as a linear combination of the Young projectors again. So you can and in this way you can evaluate the fidelity of this estimation by using in terms of the bilinear form of this parameter again. Okay, and by using this covariant protocol, I will show the conversion between these covariant protocols. So, okay, as I said, for the port-based teleportation and unitary estimation, basically they are given by, they are represented by a very nice form by using the parameter W or V. And if you calculate this bilinear form, actually which was given by the previous works, the matrix corresponding to this bilinear form also has a very nice structure. And if you define the R matrix, which takes 2 Young diagrams, and this R matrix takes a value 1, if 1 Young diagram is given, it's obtained by adding 1 box to the other Young diagram like this. Then we can represent this matrix as R transpose R, and this matrix as R transpose. So if we consider the maximization problem of this bilinear form, basically this reduces to the maximal eigenvalue problem of these matrices. But due to these forms, this reduces to maximal singular value problem of R matrices. And since they are and in this form, we can show the equivalence between these fidelities. And it's just for the fidelity, but we can also show that maximal eigenvectors can also be transformed in a very nice way, just applying R. So in this way, we can show the conversion of the protocols. Okay, so let me conclude the talk. So in this talk, we show that there exists an equivalence between port-based teleportation and unitary estimation if you choose a parameter in a suitable way. And basically this is a take home. But we have several future works, and basically, so in our work, we constructed the conversion of the protocol via the covariant protocol, which utilizes, this was the core idea of our construction. But covariant protocol, in some cases, may not be quite good in terms of some resources, like a number of qubits or entanglement, for instance. And for instance, for the unitary estimation, it is known that there exists some adaptive unitary estimation protocol using no auxiliary qubits. So it's very efficient in terms of the number of qubits, which is shown in this paper. But for the covariant protocol, covariant protocol should utilize the input unitary in parallel always. So you need to prepare a lot of qubits at once. So these are different, and in some cases, adaptive strategy may be better. So our future work is to construct a more efficient conversion between unitary estimation and the port-based teleportation, in a sense that if you have efficient construction of the, say, port-based teleportation, can we construct an efficient protocol for the unitary estimation, that kind of thing. Yeah, but this is it, and thanks for listening.
Thanks, Satoshi. Questions? I can.
So do you think that it's possible to somehow extend these results to estimation of non-unitary channels, so to find some correspondence between some kind of similar protocol to this port-based teleportation and more general channel estimation?
Mm-hmm. Yeah, thanks for a question. For now, I don't have any good candidates for the teleportation side because our construction is crucially relies on the structure of the unitary group. And if you extend to non-unitary one, so for instance, our construction is in terms of basically the Young diagram. And the reason why Young diagram appears is due to the unitary group symmetry. But if you don't have this kind of symmetry, then yeah, it's not so trivial how to have a generalization. But I think it's a very nice question. Thanks.
Other questions? I actually have one. So Michael and others have looked at this multiport-based teleportation recently. Is there some equivalent task on the unitary estimation side for this?
Yeah, thanks. Yeah, so I think it's a very nice question. I have also considered about that, but yeah, for now I don't have a very good answer. But I guess the multiport-based teleportation will be, or may have some connection if you want to estimate multiple unitaries. So for now, we just have a single unitary, and you want to estimate single unitary. But if you want to estimate the multiple unitary, for instance, if you or even single unitary, but change the fidelity measure. So for now, sorry. So for now, we consider the fidelity measure like this. But this fidelity measure might be good if we want to utilize estimated unitary once. But if we want to utilize estimated unitary a lot of time, the natural figure of merit will be multiply fidelity to be. For instance, if you want to utilize estimated unitary k times, the natural figure of merit to have a k times, fidelity to the k kind of thing. And I guess if you consider this kind of generalization, maybe there is some connection to the multiple teleportation.
Okay, if there are no more questions, then let's thank Satoshi again.
Thank you.